Welcome back to this module on pipelining. In this lesson I will describe some features of the canonical 5-stage pipeline and explain what pipeline hazards are. Now that we have seen a sketch of the pipeline data path, we can explain in retrospect certain features of the Mips instruction set architecture that have been included to make pipelining easy. First, all Mips instructions have the same length, namely 4 bytes. This allows the PC to be incremented by 4 before the instruction is decoded. If instructions could have different lengths, as in the x86 instruction set architecture, we would first need to decode the instruction to determine its length before incrementing the PC or do something more advanced. Second, Mips supports only a few instruction formats, 3 to be precise. As a result, instruction decoding can be performed normally in a single clock cycle. Furthermore, the source registers are always in the same place in the instruction format. This allows reading them before the instruction is decoded. If they are not used, the data read is simply ignored. Third and finally, only loads and stores access memory. To process data in memory, it needs to be loaded into a register first. To explain why this makes pipelining easy, let's assume by contradiction that our processor would support an add memory instruction where one of the source operands can be a memory location. For example, the add mem R1, R2, 4, R3 shown here would mean R1 becomes R2 plus the contents of the memory location whose address is given by 4 plus R3. To support such instructions, we would need at least an additional execute stage, as shown in this pipeline diagram here. The first execute stage is needed to calculate the effective address, in this case 4 plus R3. Then we can access memory to load the data at that address. And then we need an additional execute stage to add the data loaded from memory to, in this case, R2. This makes the pipeline longer and the cost of emptying or flushing the pipeline, which, as we shall see, is sometimes required, higher. A saying goes, if it seems too good to be true, it probably is. That saying also applies to pipelining. Although pipelining is an excellent technique to accelerate a processor, there are still some challenges we need to solve. The first challenge is called structural hazards. Structural hazard means that the hardware cannot support the combination of instructions we want to execute in the same clock cycle. The second type of hazard is called a control hazard. A control hazard occurs because a branch is fetched in the first stage as any other instruction, but only take effect at the end of the fourth stage during the mem stage. At that time, 3 other instructions have already entered the pipeline. We need to solve this somehow. The third type of hazard is called a data hazard. It occurs because the register file is written in the 5th stage, the write-back stage, while it is read in the 2nd stage, the ID stage. That means that if an instruction uses the result of a previous instruction, as in this example, it will read old or stale data as it is now. In this example, the first instruction, add R1, R2, R3, writes register R1, and the second instruction, add R4, R1, R1, reads it. As the processor is designed now, the second instruction will read old data for R1. Clearly, we have to fix this. This completes this lesson. Thanks for watching. In the next lesson, I will describe what structural and data hazards are and how they can be solved. Hope to see you back.